Let me welcome you to this lecture. We have been looking at the chemistry of boron, and so far we have learned about a very important class of compound formed by boron. That is, we have learned about metal borides, and we have also looked at some of the important applications of metal borides because of their very unusual and useful properties. So let us now proceed further and then learn about another important class of compound formed by the element boron. So we'll now learn about the chemistry of hydrides of boron. Because of the similarity of the hydrides of boron with the hydrides of carbon, that is hydrocarbon, these hydrides of boron are named as boranes. So these are hydrides of the element boron. There are a large number of hydrides of boron or boranes are already reported, and many of these compound structures have also been elucidated. And the most important aspect of these compounds is the kind of structures that are observed in case of boranes, which is not observed for hydrocarbons. As in this case, in case of boranes, one sees the structures that one observes are cage kind of structures, or nest kind of structures, or spider web like structures are observed. So in terms of structural complexity, boranes are much more diverse as compared to hydrocarbons. So now the chemistry of boron, because of the structurally integrating nature of these compounds, as well as the unusual bonding that we observe in boranes, essentially drawn a lot of attraction in recent years. And in fact, 2 Nobel Prizes in chemistry were awarded due to developments made in the chemistry of boron. That is, in the year 1976, William Lipscomb was awarded Nobel Prize in chemistry for extending the concept of bonding for boranes, because as we have already mentioned, the normal or conventional bonding definition of a chemical bond that we are familiar with is not valid in case of boranes, and Lipscomb did contribute towards improving our understanding of bonding in boranes, and that is why he was awarded Nobel Prize in chemistry. The second Nobel Prize in chemistry in this area was awarded just 3 years later in 1979. That was awarded to A.C. Brown. And A.C. Brown discovered this hydroboration reaction that you have already learned, which is a very important organic synthetic tool of by using the diborane molecule as the reagent. So that is why A.C. Brown was awarded a Nobel Prize in chemistry. So now we will, during this, while learning about the hydrides of boron, we will look at the structure of these compounds and how to rationalize these structures in terms of the number of electrons that each of these boron molecule has, or we will count the number of electrons, and then we will be able to predict the structure of these boranes, and also we will be able to categorize these boron molecules in different classes of compounds based on the structural type of these compounds. But before we do so, let us try to understand what is unusual about bonding in boranes and why we cannot use our conventional definition of a chemical bond to describe bonding in boron. So for this, what we will do is that we will look at the structure of diborane molecule and then see if it is possible to use or understand or describe the bonding in diborane by using the conventional uh, definition of chemical bond or not. So the diborane molecule, that is formula is B2H6. One may consider it to be a dimer of the simplest borane, that is BH3, which cannot be isolated, but instead we can isolate the dimer, that is B2H6. Now the structure of this compound was obtained sometime in 1949. So the structure of diborane is this over here. So it has 4 terminal pH bonds are present, and then there are 2 hydrogen atoms are essentially they act as bridging hydrogen atoms and bridges the 2 boron atoms here. So the boron atoms are essentially sp3 hybridized, as the geometry around the boron centers for both of these 2 boron centers is roughly tetrahedral in nature, and the bond angles, if you look at the bond angles, this bond angle, the HVH bond angle here is 122 degree, while this particular bond angle, that is the inner HVH bond angle, is 97 degree. So then there is another important structural parameter that we should look at, that is the outer BH bond, that is terminal BH bond. The bond length is 119 picometer, while for the inner BH bond or the bridged BH bond, lengths are equal to 137 picometer. So what we see here is that the outer BH bonds are much shorter than the this bridge BH bonds. So the bond order must be higher for the terminal BH bonds as compared to the bond order for the bridge BH bonds. Now let us look at the electronic configuration of boron and then see if why we cannot use the conventional definition of chemical bond to describe the bonding in diborane. So let's look at the electronic configuration or outer cell electronic configuration of boron. So that is 2s orbital and 2p orbital. That is, electronic configuration is 2s2 and 2p1. As the boron centers here are roughly sp3 hybridized, or as we can see that there are 4 sigma bonds each of these boron atom forms. So the boron atoms undergo sp3 hybridization. So what we can do is we can write the 4 sp3 hybridized orbitals and also fill the electrons that are present in each of these boron atoms. Since there are 3 electrons, we can fill 3 of these sp3 hybridized orbitals are occupied by one electron, while one of the sp3 hybridized orbital remains empty. Now, since boron atom is involved in covalent bonding with 4 of the hydrogen atoms, but it does not have enough electrons, or it does not have 4 electrons in the 4 sp3 hybridized orbital to form 4 covalent bonds on its own. So that is why one cannot, or we have difficulty to explain the bonding in diborane by using the conventional VSEPR valence bond theory, and instead we will have to extend this idea a little further. And in fact, there was some attempt to rationalize the structure, this diborane structure, by using the valence bond theory itself. And what one did is that a few resonance structures were proposed for formation of, or for observation of this sort of structures, even while maintaining or while trying to keep the valence bond definition of chemical bond intact. So what kind of resonance structures that we can draw. There's this sort of resonance structures. So combination of two BH3 groups, and you can say that there is weak interaction between the hydrogen atoms of these BH groups over here, and then we can also write another one for the counterpart for this one, that is this sort of a resonance structure. Then we can also have resonance structures or salt-like resonance structures where one of the boron atoms become tetravalent in this way. So it is BH4 unit, while the other boron center, the BH2 group, which is cationic in nature. And then we can also write the counterpart for this one. That is, we can make the first boron atom cationic, and the second one we can make it as anion. So this is the most rudimentary way or most basic way to describe the structure or rationalize the structure of diborane by using balanced formed approach. But this approach hardly do justice to the structure, because we cannot rationalize why the diborane molecule as such is electron precise. It is not electron deficient, but as per this particular, if these resonance structures have to be correct, then the diborane molecule will be electron deficient, because we have trivalent boron centers in this. Are part of the resonance structures that we write for this particular approach. So that is not correct, and some more ideas or some more ways to rationalize the structure of diborane were also proposed. So another one which is interesting in terms of the idea is that if you look at the B2H4 2 negative ion, or if you count the number of electrons for this B2H4 2 negative ions, what we will find is that the number of electrons that we have for here is equal to the number of electrons that we have in case of C2H4, because carbon has one more electron as compared to borons. So that is why when we put two negative charges on top of it, so this becomes isoelectronic with the ethylene molecule over here. And we know that isoelectronic molecules are also isostructural. So that is why the structure of B2H4 2 negative should be similar to the structure of ethylene molecule. Now we know the structure of ethylene molecule, that is, the carbon atoms are involved in double bond, and the pi cloud essentially lies above and below the sigma bond clouds, and which is in a plane perpendicular to the sigma bonds essentially. So this is what is the structure of ethylene. So now we can also draw the structure of B2H4 2 negative. And now what we can do is that the two negative charges, we can say that the negative charges essentially lie above and below the plane formed by these BH and BB sigma bonds here. So now what we do, if we hypothetically assume that we add two protons to this B2H4 2 negative ion to make B2H6, then what is going to happen is, or what we will end up with is the structure of diborane, because what we will have is this negative charge here, and the electron, each electron from hydrogen atom essentially, we do not have electrons in the hydrogen atoms because we are adding protons here. So H plus and H plus. There are two negative charges as well as there are two electrons that are there for this BB linkage over there. So there are total 4 electrons are present, and these 4 electrons will now be able to form this BHB two bonds or linkages, bridges. That is BHB, this BHB linkage and this BHB linkage are essentially formed by total 4 electrons. So each of these linkages are essentially formed by 2 electrons each. So this is formed by 2 electrons and this is also formed by 2 electrons. So this particular approach or this particular idea to rationalize the structure of diborane looks very absurd in fact, because what we have done is hypothetically we have added protons to the charges over here, and we have assumed that this particular species will have structure similar to the structure of ethylene. But then this gives some idea or for us to eventually come up with an approach which describes the bonding in diborane more accurately, because let us draw the sp3 hybridized orbitals on each of these boron atoms and look at the structural picture once again. So these are the sp3 hybridized orbitals on the boron centers, and let us also fill the electrons on these sp3 hybridized orbitals. Now we know these terminal BH bonds in diborane, they are shorter, has higher bond order as compared to the bridged BH bonds over here. So then these must be these terminal BH bonds must be normal BH single bonds formed by the sp3 hybridized lobe of boron and 1s orbital by overlap of this sp3 hybridized lobe of boron and 1s orbital of this hydrogen atom. So when they overlap, the covalent bond, pH covalent bond is formed by sharing of these two electrons between the boron center and the hydrogen center. So these are conventional BH bonds or conventional bonds that we are familiar with, these terminal BH bonds. But then when we look at the bridge BH bonds, let us draw the hydrogen atoms or the 1s orbital of the hydrogen atoms with the electrons in them. So now what we have is these BHB linkages are now formed, we see, by overlap of 3 orbitals, that is an empty sp3 orbital, hybridized orbital of one of the boron center, 1s orbital of the hydrogen atom, and a filled sp3 hybridized orbital of another boron center. So now what we have here, we do not describe these BH bonds as individual covalent bonds or individual 2-center 2-electron covalent bonds. But instead what we do is that we describe this bond as 3-center 2-electron bond. So this is one bond is formed by sharing of 2 electrons, because 1 electron comes from here, this hydrogen, and 1 electron comes from the boron center over here. And this linkage, essentially this 3-center 2-electron linkage, holds together or connects this boron center, this hydrogen atom, and this particular boron center over here. So it is essentially it holds together 3 atoms and 2 electrons are there for formation of this covalent linkage. So this is a 3-center 2-electron bond, and this new concept has to be given in order to rationalize the structure of diborane. So similarly for the other BHB bond linkage also, we have one of the filled sp3 hybridized orbital here, one of the hydrogen 1s orbital with 1 electron in it, and another empty sp3 hybridized orbital. This forms the second BHB linkage. So we we can also draw this BHB linkages instead of drawing it in this way, because this is one bond, not two bonds. What we can do is that we can draw this bond in this particular fashion. So hydrogen atoms. So this sort of bonds, we also describe these bonds as banana bonds because they look like the banana, and they are essentially, this is one bond, this is one bond, one 3-center 2-electron bond, this, and this is another 3-center 2-electron BHB bond, and this is how we extend the conventional definition of bond. That is, we know, we are familiar with bonds which are formed by two atoms or formed between two atoms by sharing of 2 electrons. Now we have a bond here which connects 3 atoms and by sharing only 2 electrons again. So this is a special type of bond, and we can extend this even further into multicenter bonds, or which bonds which can hold together more than even 3 atoms, say, and then only 2 electrons are shared. So these sort of bonds are also full center 2-electron bonds are also known. Now what we will do is that we will rationalize this sort of bonding in terms of molecular orbital theory, because molecular orbital theory only allows us to define this sort of bonds. So how this BHB linkage is formed, that we will see by drawing the molecular orbital picture of this BHB, 3-center 2-electron BHB linkage. So now what we will do, we will draw the molecular orbital picture. So this is the energy scale, and what we have in this BHB linkage, there are 2 orbitals of 2 different boron centers are essentially involved. Now sp3 hybridized orbitals, let's call these orbitals as psi b1 and psi b2. One of these sp3 hybridized orbitals is essentially occupied and the other one is empty. So let's fill psi b1 while psi b2 is empty. So these are the 2 boron centers here. So let us when these 2 boron centers combine, the wave function for these 2 boron centers will eventually combine, or we can do something, a mathematical procedure known as linear combination of atomic orbitals. So these sp3 hybridized orbitals will essentially, we can do linear combination of these 2 orbitals, and that will give us 2 linear combinations, because when we combine 2 atomic orbitals, we get 2 linear combination. The first linear combination is going to be where there is positive overlap between the 2 orbitals, that is psi b1 plus psi b2, and in the second case, there is negative overlap between the 2 orbitals, that is psi b1 minus psi b2. So this combination can be found out by doing a mathematical procedure known as linear combination, a symmetry adapted linear combination of atomic orbitals, and you will learn it while learning about the symmetry procedures. Then we have the atomic orbital for hydrogen. Let's write the atomic orbital for hydrogen here. So that is psi h, and which is again occupied by 1 electron over here. So then these linear combinations are going to combine with the atomic orbital. We'll do another linear combination, that is with the linear combination of this linear combination with the atomic orbital of hydrogen. And then what is going to happen is that, see, when we can do this sort of, or when we can form this sort of molecular orbitals starting from atomic orbitals, 3 conditions must be fulfilled. These conditions are essentially that the energy of these atomic orbitals must be similar. So similar energy, which is true here, because the energy of the 2s and 2p orbital of boron is not very largely different from the 1s orbital of hydrogen. So there is, the combination can occur to form, these atomic orbitals can combine to form molecular orbitals. Similar energy. This is the first condition. The second condition is that there must be some spatial overlap between the atomic orbitals to form the molecular orbitals. So overlap is a necessary condition. Orbitals must overlap to form molecular orbitals. And the third condition, which is again very important for formation of atomic or molecular orbitals starting from atomic orbitals, because we do the procedure itself is known as symmetry adapted linear combination. If the symmetry of the atomic orbitals are not correct, or if they are not compatible with each other, then eventually no linear combination will result after we do the symmetry adapted linear combination. So that is why this symmetry must be compatible for formation of molecular orbitals starting from a set of atomic orbitals. So symmetry restrictions are there. So then, because of the symmetry restrictions, eventually only this particular linear combination will form molecular orbital by combination with the atomic orbital of hydrogen, and this will eventually give us the molecular orbitals for BH V linkages. So that is tri bonding. We have this molecular orbital will combine with this molecular orbital and will result or will give us two molecular orbitals, one bonding and one anti-bonding. So this is psi anti-bonding. So we can draw it in this way. And then this combination, linear combination, psi b1 minus psi b2, because this cannot undergo linear combination with the atomic orbital of hydrogen over here, this will remain as psi non-bonding because it does not participate in bonding essentially, and that is why it remains as non-bonding molecular orbitals. So now let us fill the electrons in these molecular orbitals. One electron from psi b1 plus b2 and one electron from the hydrogen or atomic orbital over here. So we have two electrons in the bonding molecular orbital, and the non-bonding and anti-bonding molecular orbitals remain empty. So now what we see is that the bond order for this BHB linkage, that is 3 center 2 electron BHB linkage, is going to be equal to 1, and this is how we can describe this BHB linkage or BH 3 center 2 electron BHB linkage by using the molecular orbital theory. So this is how we can describe, or this is how we can rationalize the formation of this structure of. We can rationalize the structure of diborane even when boron does not have enough electrons to form 4 single bonds with the hydrogen atoms in the structure of diborane, as we see in the structure of diborane. Right? We can explain this formation of the structure of diborane by invoking the concept of multicenter bonding, or invoking the concept of this 3 center 2 electron bonds that reach hydrogen atoms, or the BHB linkages essentially are formed by multicenter bonding. So this is how we describe the bonding in diborane. And what is interesting is that in case of diborane, we see only one type of 3 center 2 electron bonds, and the other BH linkages, that is the terminal BH linkages, are essentially 2 center 2 electron conventional bonds. But when we go for higher boranes having higher number of boron atoms as well as hydrogen atoms, and we will learn about these boranes, of course, in the next few lectures. In these higher boranes, we see also another type of multicenter bonding, that is BBB multicenter 3 center 2 electron linkages are also observed in case of higher boranes, and we will discuss talk about these kind of bonds in the next few lectures. So with this, this essentially brings us to the end of this lecture, and what we have learned during this lecture is how one can describe the bonding in diborane molecule, or how in case of the borane molecules, in case of the boranes, boron atoms instead of being electron deficient, instead of having only 3 electrons in the valence shell, boron is able to form uh, electron precise molecules, not electron deficient molecules. How it can the boron atoms can fill the can can have uh, an octet of electrons in spite of having only 3 electrons on its own. So in the next few lectures, we will describe talk about more about these boron molecules or the structure of these boranes, as well as how to rationalize or how to predict the structure of the boranes by just simply by counting the number of electrons in these boron molecules. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.